56 shells per second, and a solid wall of fire that left low-flying aircraft without a single chance to survive. Friends, meet the ZSU-23-4 Shilka. It was created as a terror of the skies, but in the end, it became a legend under completely different conditions. Why did this system, developed solely to counter aviation, earn the terrifying nickname Shaitan Arba on the ground? And why was its fire feared more than heavy artillery? How did simple equipment from the far-off 1960s manage to fit into the era of high-tech drones and low-flying missiles, remaining in the service of dozens of countries? And what is the secret formula of its phenomenal survivability? Watch this video to the end. Today we will analyze the unique features of this legendary machine, look into its history, and find out why the Soviet Shilka still has exceptionally sharp teeth. Let us begin. The beginning of the 1950s. The Korean Peninsula. Anti-aircraft artillery crews look into the sky and see what their fathers did not see just one generation ago. A jet aircraft sweeps over the positions faster than the gunner can turn the barrel. A second of delay and the target is already out of reach, and the next attempt to hit it becomes meaningless. The old methods of guidance relied on the human eye, the human hand, and human reaction speed. Against the piston engine machines of the previous decade, this scheme worked well. Against jets, almost not at all. The difference in speeds was not by times, but by an order of magnitude. Much like if a person with a stone in his hand stood by the side of a high-speed highway and tried to hit a passing car exactly, he has less than a second for the throw, and the car is already almost hidden around the bend. This was the very problem faced by anti-aircraft artillery crews on both sides of the Korean conflict. Defense analysts recorded the same thing. The number of successful hits on low-flying jet targets was extremely low. It was not about the quality of the guns, it was about the very scheme, eye, hand, barrel, which physically could not keep up with the new speed. What was actually happening in those few seconds while the target was approaching the position? First, the gunner had to spot the aircraft. Then, by eye, estimate the range, speed, and direction of flight. After that, turn the gun, take the lead, and open fire. Each of these stages took time. The jet aircraft left almost none of this time. By the middle of the conflict, it became completely clear. The old formula of anti-aircraft defense was obsolete not partially, but completely. What was needed was not a refinement of existing guns, but a fundamentally different approach to the task itself. Engineers had to solve a problem that on paper looked almost unrealistic. Remove the person from the decision-making chain where the count goes to fractions of a second. Replace the gunner's eye with a radar station. Replace his hand with automation. And assemble from all this a single mechanism working without delays and without the right to miss. It sounds simple. In practice, not a single country had built such a machine in those years. Only a few years would pass, and a Soviet designer would be assigned a task that would become the main business of his entire engineering life. But before talking about the solution, it is worth understanding one simple thing: the price paid for every missed second in those years when the sky ceased to be a safe place for ground positions. 1957. Nikolai Alexandrovich Astrov, a designer with considerable experience in creating light armored vehicles, is assigned a task for which at that time there was simply no ready-made solution. A machine is needed capable of finding jet aircraft, aiming the gun at them, and opening fire faster than a person could do it. That is, a machine in which a person is assigned not a primary, but an auxiliary role. For the design school of the late 50s, this was almost a revolution in the very logic of design. Previously, weapons were built around a person, under his hand, under his eye, under his reaction speed. Now it was required to build a system where the decisive role is played by automation, and the person only controls the process and, if necessary, interferes. At the first discussions in the design bureau, the idea caused outright skepticism. Some engineers insisted that it was impossible to combine a radar station, a computing device, and an artillery system in one compact hull without losing weight, speed, or reliability. Others doubted that such electronics of the 40s and 50s were generally capable of working in conditions of shaking, dust, and temperature changes on the march. Astrov approached the task from the other side. Instead of trying to improve the existing anti-aircraft system, he proposed to design the machine anew, starting not with the gun, but with the target detection system. The logic was simple. If the human eye no longer keeps up, it must be replaced with something that sees further and reacts faster. And here it is worth pausing on one detail that is rarely spoken about. At about the same time, other countries were trying to solve similar problems. Developments of self-propelled anti-aircraft systems with radar guidance were carried out in parallel in several design schools at once, but most early attempts ended in one of two outcomes. Either the machine turned out to be so heavy and bulky that it lost the main advantage of anti-aircraft technology, mobility, or the electronics turned out to be too temperamental for field conditions and required constant maintenance in workshops and not on the march. The task that Astrov received was precisely to avoid both of these traps simultaneously. The machine had to move along with the column without falling behind, and at the same time see the target at a distance inaccessible to the human eye and shoot with an accuracy inaccessible to the human hand. The development stretched over several years. There were three key nodes: the radar station, the computing device, and the artillery part. Each of them individually was a complex engineering task. But the real difficulty lay not in themselves, but in making these three completely different mechanisms work as a single whole, without delays between target detection and opening fire. It was with the solution of this task that the real history of the machine began, and it began not with barrels and not with armor, but with the part that would later be called its eyes. The heart of the new machine was the radar complex named Tobol, which received the index RPK2. This stands for Radar Instrument of Complex Number 2. It was this station that was to replace the human eye where the human eye physically could not cope. The task before the developers was concrete. The station had to detect a low-flying air target at a distance of up to 20 kilometers, and at the same time fit into a hull that would remain light enough for a mobile armored vehicle. 20 kilometers is a distance that a jet aircraft at extremely low altitude covers literally in a matter of a few dozen seconds. That is, the crew had time not just to notice the threat, but to manage to prepare for the meeting long before the sound of the engine became audible to the human ear. And here it is important to understand the difference between the old and the new approach. Previously, the gunner reacted to what he already saw with his own eyes, a silhouette in the sky and approaching sound. The radar worked completely differently. It saw the target long before it entered the zone of visual contact of the crew and transmitted the data directly to the computing device. If we translate this into the language of everyday images, it is like if a person could calculate in advance the trajectory of a ball flying from the other end of the stadium even before this ball left the player's foot, and calculate not approximately, but with an accuracy sufficient for a shot. The computing device took the radar data, range, speed, direction of target flight, and in real time calculated the lead point. That is, not where the target is located now, but where it will be at the moment when the shell reaches it. Previously, the gunner estimated this lead by eye, relying on experience and intuition. Now the machine calculated it, and did it several times faster and more accurately than a human. It is worth noting one important nuance. The station could work in two modes: track the target automatically, trusting the entire process to electronics, or work in a semi-automatic mode, when the crew could correct the guidance manually. Such flexibility proved critically important because the electronics of the middle of the 20th century, with all its advantages, sometimes failed in difficult weather conditions or in the presence of interference. The engineers perfectly understood the limitations of the technologies of their time and built into the machine the ability to return control to a person at any moment if the automation did not cope. But the very idea to replace the gaze of a person with the gaze of a machine that does not blink, does not get tired, and does not lose sight of the target was breakthrough at that time. The radar became the first link in the chain that had to work without pauses, from detection to shot. However, accurate information about the target itself decides nothing if the weapon is not capable of reacting to it as quickly as the radar manages to find this target. The radar found the target. The computing device calculated the lead. The remaining question was, what exactly to fire in order to guaranteed hit an aircraft moving at extremely low altitude with great speed? The answer was 4 automatic guns of 23mm caliber, which received the designation A018, also known by the index of the main rocket and artillery directorate as 2A7. The idea to combine 4 barrels at once into a single block was born not from a desire to look impressive, it was a direct consequence of the same problem: time. One barrel, even the most rapid firing, physically cannot create a sufficient density of fire in the air to guaranteed hit a fast-moving and maneuvering target in those few seconds that it is in range. 4 synchronized barrels solved this problem due to the volume of fire. The total rate of fire of the entire system reached 3,400 rounds per minute. To understand what this means in practice, a simple comparison is enough. An ordinary adult makes from 12 to 20 breaths per minute. While one such breath lasts, the system managed to produce not 1 and not 10, but about 200 shots. The automation of each barrel worked on the basis of the energy of powder gases, a principle familiar from many types of automatic weapons of that time, only brought to ultimate reliability and speed. All 4 barrels moved synchronously, aiming at the target simultaneously, according to the data that came from the radar through the computing device. Guidance of the entire artillery part was carried out not by the muscular strength of a person, but by hydraulic actuators. This was another fundamental step away from the old guidance scheme. The barrels turned and rose so quickly that the speed of their movement exceeded the capabilities of any person turning a handwheel manually. The ammunition capacity of the machine was divided into 2 types of shells: high explosive fragmentation incendiary and armor-piercing tracer, which allowed for effective work against both lightly armored and unarmored air targets. The calculation of the entire system was built on one simple principle: to create at a specific point in space, where in a fraction of a second the target would enter, such a density of fire at which the chances of missing tend to a minimum. On paper, everything looked convincing. The calculations agreed, the characteristics of the radar and the artillery part corresponded to the task. But one thing is a theoretical model on the drawings of a design bureau, and quite another is a real check where the price of an error is measured not by a line in a report, but by whether the shell hits the target or not. Exactly such a check awaited the machine ahead. Proving ground tests of the new machine began in the late 50s and stretched for several years. Everything was checked: the reliability of the radar station under different weather conditions, the accuracy of the computing device, the synchronicity of the operation of the 4 barrels, the survivability of the chassis on rugged terrain. Special attention was paid precisely to the link between the 3 main nodes of the machine. It was not enough to check that the radar finds the target. It was necessary to make sure that the data from it reaches the artillery part without delays capable of neutralizing the entire advantage of the early detection system. At test firings at towed targets imitating low-flying air targets, the results exceeded the expectations of the developers themselves. The density of fire created by the 4 barrels, with precise guidance according to the radar data, turned out to be exactly the solution for which the entire development was started. The commission that accepted the machine into service formulated the conclusion extremely clearly. A repeated approach of an aircraft to a position covered by such a system becomes so risky that one should forget about it in principle. The old tactics, in which the pilot could calmly fly around the position in a circle and attack from a more convenient angle, stopped working. In 1962, the machine was officially accepted into service under the designation ZSU-23-4, which stands for Self-Propelled Anti-Aircraft System of 23 mm caliber with 4 barrels. A little later, the unofficial name Shilka was fixed behind it, in honor of the river of the same name in Transbaikalia, according to the tradition of assigning the names of rivers to some specimens of Soviet technology of that period. On paper and at the proving ground, all indicators looked excellent. The specialists who participated in the tests were sure that the machine completely solves the problem with which the forces faced back during the Korean conflict. The jet speed of the aircraft was no longer invulnerable to ground defense. But any proving ground conclusion has one significant drawback. A target on a tow rope does not maneuver, does not try to evade, and does not act on its own initiative. The target is not afraid and does not make decisions. The real test of the machine awaited it not at the proving ground, where all parameters are known in advance, but where decisions are made by a living pilot trying to survive and win in a real aerial confrontation. And this test would happen not months after acceptance into service, but years later, thousands of kilometers away, on a border that at that time was considered tense every day. The autumn of 1969. The border between Egypt and Israel on the Sinai Peninsula. By this time, Israeli aviation had been used to working at extremely low altitudes for several years, with virtually no consequences. The tactics were simple and proven. Approach at extremely low altitude, below the zone of action of most anti-aircraft means, strike and leave before the ground crews have time to react. For years, this scheme worked almost flawlessly. And then something changed. A pilot, used to an empty sky over positions, suddenly sees a dense wall of tracers in front of him, where even a month ago there was nothing but sand and rare flashes of single shots. Moreover, this wall appears not after the aircraft has already flown over the target, but practically immediately, as if someone knew about his approach in advance. The fact of the matter is that this was exactly how it was. The radar station detected the target at a distance inaccessible to the human eye, long before the aircraft entered the zone of visual contact of the crew. By the autumn of the same year, ZSU-23-4 systems began to appear on Egyptian positions, and the first clashes with them showed the old scheme of extremely low flight no longer guarantees safety. Systematic, confirmed data on the number of shot-down machines of the Skyhawk type in this period has been preserved little. The archives of those years, for objective reasons, are incomplete, and part of the episodes remain the subject of disputes among historians. But one fact remains indisputable and is confirmed independently from both sides of the conflict. Israeli aviation losses at low altitudes increased noticeably precisely in the period when the new technology appeared on the positions of the opposite side. And they increased so tangibly that the command was forced to revise the very tactics of flights on this sector of the border. Pilots had to abandon the habitual scheme of extremely low flight and raise the altitude of the attack, losing in the process part of the surprise effect for which low altitudes were originally used. Think for a second what this meant in practice. Tactics that for years were considered almost win-win turned into a source of unjustified risk in a matter of weeks. And the reason for this was one specific Soviet development, before this moment not once checked in real operational conditions. This was the first serious exam for the machine born on the drawings of the Astrov Design Bureau. In this exam, it passed so convincingly that already in a few years it had to pass a check of a much larger scale. Only 4 years passed after the first clashes in Sinai, and in the autumn of 1973, a much larger scale conflict unfolded on the same theater of confrontation, where the system had to prove that Sinai was not a coincidence. By this time, ZSU-23-4 stood in service already in a much larger quantity, covering positions denser and over a greater extent of the front, and the effect of this became noticeable almost immediately. Israeli aviation losses at low altitudes in the very first days of the conflict turned out to be so tangible that the command had to literally, on the fly, revise the habitual schemes of approach to the target. The tactics of extremely low flight, which for decades had been considered the gold standard of evading ground defense, now turned into a direct threat to the crew. It was not about one successful system on one position. It was about the system. The radar detected the target many seconds before the approach, the computer instantly calculated the lead, and the 4 barrels created such a density of fire in the air that the chance of slipping through unnoticed fell sharply. It was the combination of these 3 elements, and not any one of them individually, that became the decisive factor. One speed of fire alone, without early detection, would not give such an effect. One radar alone, without dense fire, also would not solve the problem. Only together, working as a single mechanism without pauses between links, these elements changed the very logic of air engagement over positions. And here a question arises that is worth asking honestly. What if the opposite side had more time to adapt? The answer to this question lies on the surface if you look at the calendar. Less than 4 years passed from the first reports of the new threat in Sinai in the late 60s to the start of the full-scale conflict in 73. For the revision of the tactics of an entire branch of service, for the retraining of pilots, for the development of countermeasures, this is a vanishingly small period. Aviation tactics do not change in months. They change over years, through the analysis of each episode, through the development of new instructions, through the change of habits that have eaten into the training of pilots over the previous decade. There was simply not enough time for this. By the end of the conflict of 73, the fact was recognized by almost all analysts without exception, regardless of on whose side they conducted the analysis. The system, designed for a specific task of the Korean conflict of 20 years ago, completely justified the calculations of its creators already twice in a row, in 2 different conflicts, with a difference of several years. But a check by one type of terrain does not mean a check by all. The sands of the Middle East are an open space where the radar sees the target from afar without obstacles. A completely different story awaited the machine where the horizon line hides behind each turn of the gorge. The end of the 70s, Afghanistan, a landscape completely opposite to the flat sands of the Sinai Peninsula. Narrow gorges, stony slopes, shelters behind boulders and in crevices of rocks, where the horizon line constantly hides behind the next turn. The system, designed to detect jet aircraft at a distance of 20 kilometers, was brought to a locality where this distance itself was often physically unattainable. The mountains simply closed the view to the radar already after a few hundred meters. It would seem that in such conditions, the main advantage of the machine should have turned into a useless option. The radar, for the sake of which the entire construction was created, turned out to be practically unclaimed in the mountain relief. And here happened what even the designers themselves did not assume. The machine, deprived of the opportunity to use its main advantage, unexpectedly found a completely different application and turned out to be irreplaceable in it. 4 barrels, capable of creating the highest density of fire, did an excellent job not only with aircraft. They worked with the same efficiency on slopes, on crevices, on any shelters where an ambush could be located. Neither a machine gun nor a mortar of that period could create a comparable density of fire at such a distance in the same short time. A machine gun fired from 1 barrel, a mortar required time for sighting and correction. The system, in the literal sense of the word, covered an entire section of the slope with fire in a matter of seconds, without long preparation. The crews quickly learned to work without using the radar at all, conducting fire visually or by target designation from the ground from the accompanying infantry. The accuracy of an individual hit in this mode, of course, was inferior to automatic guidance, but the density of fire remained the same, and this was often enough to disrupt an organized attack from ambush before it even had time to unfold in full force. Stone chips raised by bursts along the slope flew in all directions, with no less effect than the fire itself. Any shelter from behind which firing was conducted ceased to be a shelter in principle in a few seconds. Local residents and participants in ambushes quickly learned to distinguish the characteristic sound of the work of 4 barrels by ear, long before the appearance of the machine itself in sight. And this recognizable sound became the reason that the system received its own name in the mountains, a name that more eloquently than any technical characteristics described the impression it made on those who found themselves under its fire. The nickname Shaitan Arba, which the system received in the Afghan mountains, translates roughly as Devil's Cart. It sounds crude, but behind the nickname is a very specific, down-to-earth meaning. Local residents and participants in ambushes describe the machine as they describe what they fear in advance, even before the direct meeting. The fact of the matter is that the sound of the work of 4 barrels was so different from the usual crackle of machine gun bursts or single mortar explosions that they learned to recognize it by ear seconds before the fire reached a specific point of the slope. It was not a single shot and not a short burst. It was a dense, almost continuous hum, as if the mountain itself began to crumble into pieces. The system crews by that time had completely adapted the tactics to mountain conditions. The radar station, for the sake of which the machine was originally designed, here most often stood idle. The mountain simply did not give it the opportunity to work at the full distance of detection. Instead, the fire was conducted visually, by direct observation, or by target designation from the ground from the accompanying infantry walking ahead of the column. And here it is worth emphasizing a point that is rarely thought about. The absence of a radar did not turn the system into an ordinary rapid-firing gun. Hydraulic guidance actuators still worked faster than a human hand. The synchronicity of the 4 barrels was still preserved. The only thing that changed was the source of target data now came not from electronics, but from the eyes of the gunner or the accompanying soldier. The tactics of use in ambushes were built on one simple principle. If there is a suspicion that an ambush is ahead, fire is opened on the entire suspicious section of the slope at once, and not on a specific detected point. Simply because waiting for the opponent to detect himself with the first shot meant missing the only real advantage, reaction speed. Participants in such operations subsequently recalled the same detail. As soon as the characteristic sound became audible from the side of the column, any active actions by the ambush, as a rule, ceased by themselves. Rising from behind shelter under such fire made no sense. the density of shooting along the slope was too high to count on a successful return shot. Rumors of such effectiveness quickly dispersed not only among infantry units, but also reached the engineering units responsible for accompanying columns through dangerous sections of the road. And there, faced with the real conditions of mountain operations, the engineers decided to go further than simply using a standard machine. They began to remake it right on the spot, fitting it to tasks that were originally not laid down in the Astrov design. Engineering units, faced with the real conditions of mountain terrain, quickly came to a practical conclusion. Since the radar station is almost not used in the mountains, and the weight and volume it occupies can be directed to something more useful here and now, it is worth removing it altogether. Field modernization was carried out by the forces of repair units right on the spot, without sending equipment to the factory. The radar block was dismantled, and the freed space and carrying capacity reserve were used to install additional armor for the crew cabin. The logic of this decision is quite simple if you draw an everyday parallel. Let's imagine an ordinary car that is originally equipped with a set of options for one operating condition, but the owner understands that he simply does not need part of these options, but acutely lacks protection in other places. Then the excess is removed, and the released weight and space go to where there will be real benefit from them. This is exactly what was done with the system. It ceased to be a full-fledged means of anti-aircraft defense in the classical sense, and turned into a specialized firing point for accompanying motor columns, where its main advantage remained the exceptional density of fire on any suspicious section of terrain along the route of movement. Such remade machines were especially valued when conducting columns through the most dangerous sections of roads, where the risk of encountering an ambush was maximum. The system moved either at the head of the column or on the most vulnerable sections of the route, being ready at any moment to open fire on both sides of the road simultaneously. In the most risky operations, such remade machines began to operate in tandem with engineering mine-clearing machines, known by the designation UR-67. While the system kept the slopes and suspicious sections of terrain under sight, the engineering machine was engaged in clearing the passage from possible mine explosive obstacles on the route. The scheme turned out to be extremely rational. One machine provided dense cover along the front and flanks, the other solved the task directly on the road itself. Together, they closed at once two main threats faced by any column on the route through a dangerous section of terrain. The machine, originally designed exclusively for the detection and destruction of air targets at a distance of 20 kilometers, by the end of the Afghan campaign actually turned into a universal tool for accompanying ground forces. The task for the sake of which Astrov created it receded into the background, and the flexibility of the design and reliability laid down by him initially came to the fore. But this chapter of the history of the system was far from the last. The next decade prepared for it a completely new type of terrain, not the open sands and not the mountain slopes, but the tight stone boxes of urban development, where the rules of applying dense fire had to be built anew. The mid-1990s, a city built with multi-story buildings, where instead of open space, there are narrow streets, courtyard wells, and dozens of windows, from any of which fire can be conducted. A completely different type of engagements compared to both the sands of the Middle East and the mountain slopes of Afghanistan. By this moment, the system, designed under the task of destroying jet aircraft, was used already far from its original purpose, and in the conditions of tight urban development, it had to find a third, completely unexpected application. The four-barrel artillery part, originally created to create a dense barrage fire in the air, turned out to be extremely effective against resistance points located in buildings. A window opening on the third floor, a stairwell, a corner of a house swept through. All this became vulnerable before the density of fire that the system could provide in a matter of seconds. The difference in the perception of the same intersection by ordinary infantry and the system crew was striking. For an infantryman, an intersection is a dangerous open zone that must be overcome by dashes, pressing against the walls and risking falling under fire from any of the surrounding buildings. For the crew, the same intersection turned into a zone that could literally be closed with one short burst on all potentially dangerous points at once, even before the infantry began to move through the open space. It was this ability to quickly suppress several firing points at once in conditions of tight development that became the main reason why the system began to be attracted to engagements in the city, although initially, not a single manual provided for such a scenario of using anti-aircraft technology. Documentary evidence of precisely systematic use has not been preserved so much. Most of the information is based on the memories of direct participants in those events. But the general picture they describe coincides in main details. The system was placed where it was required to quickly and with minimal losses suppress resistance on a specific section of the street or quarter, after which the main forces could move further with less risk. Here it is important to understand one nuance. Official instructions on the use of such technology, written back in the days of Astrov, did not provide for anything of the kind. The machine was created exclusively as a means of anti-aircraft defense, and not a single document of that era considered it as an instrument of urban engagement. But the reality on the spot, as often happens, dictated its own rules, very far from what was prescribed in pre-conflict manuals. Advancing through an area considered cleared is one of the most deceptive situations in urban engagements. Cleared does not mean safe. It means only that the main forces of the opponent have passed or retreated, but individual pockets of resistance may well remain in basements, on the upper floors, or around the corner of the adjacent house. It was in such conditions that the system began to be placed at the head of the advancing column, ahead of the main mass of technology and personnel. The logic was direct. Before the infantry entered the next quarter, dense, short fire opened on the upper floors of the surrounding buildings and suspicious points. The meaning of this technique was not to destroy the building entirely. The meaning was to suppress any possible firing point with a few seconds of dense fire before it had time to react to the approach of the main forces. Floors swept through, window openings, stair flights, all this ceased to be a safe shelter for the one who was there. The crews who mastered this tactic acted according to the same algorithm. The column stops in front of a new quarter. The system gives several short but extremely dense bursts on the upper floors and the most likely locations of the opponent, and only after that the infantry begins to move forward, already with a noticeably lower risk of meeting organized resistance. It is worth thinking for a second about this. A machine designed almost 40 years ago to shoot down jet aircraft in the open sky over the desert turned out to be an almost ideal tool for a completely different environment, engagements in tight city blocks, where it is not the detection range of the target that decides, but the speed of suppression of several points at once. Not a single engineer of the Astrov Design Bureau in the late 50s could assume such a scenario of using their development. The task they solved was related exclusively to air targets in extremely low flight altitudes of aircraft. There was simply no talk of urban engagements in those years. And yet, that very dense rate of fire, redundant by the standards of its time, laid into the design for the sake of fighting jet speed, turned out to be equally in demand in the desert against aircraft, in the mountains against ambushes, and in the city against fortified resistance points. Three completely different conflicts, three completely different types of terrain, and the same principle, again and again proving its validity. The logical question after all this sounds like this. How many more countries eventually adopted this machine, and why has it, despite its age, not remained a museum exhibit? By the beginning of the 21st century, the ZSU-23-4 was in service far beyond just the country where it was designed. The machine was supplied for export over decades, and the geography of these supplies turned out to be so wide that for many specialists in technology, this became an independent reason for study. More than 20 armies of the world continue to operate this system to this day, after more than 60 years since its adoption into service. For technology designed in an era when transistors were only just beginning to displace vacuum tubes, this is an indicator that is found extremely rarely. The reasons for such popularity are not reduced to one. There are several of them, and each individually is sufficiently weighty. First, the reliability of the design. The mechanical part, the tracked chassis, the hydraulic guidance actuators, the automation of the barrels, was built on the principle of maximum simplicity and repairability right in field conditions, without the need to send the machine to the factory for every minor malfunction. Second, the availability of spare parts. Over decades of operation in dozens of countries, an entire industry has emerged for the production of components and ammunition of compatible caliber, which makes the maintenance of such technology significantly cheaper than the purchase of fundamentally new systems. Third, and this is perhaps the most unexpected, the continuing relevance of the very principle laid down by Astrov back in the late 50s. High density of fire still remains an effective means against certain types of modern threats. And here lies a fact that looks almost paradoxical. Despite the fact that over the past decades, many far more modern air defense systems have appeared, equipped with the latest electronics and guided missiles, a number of countries consciously continue to invest precisely in the modernization of this old platform, and not in its complete replacement with something fundamentally new. At first glance, this may seem a strange decision. Why modernize technology of the pre-computer era if you can buy or develop something more modern from scratch? The answer to this question is not so simple as it seems, and it is connected with the same dense rate of fire, redundant by the standards of the 60s, which was originally laid into the design for the sake of fighting jet speed, and today turned out to be in demand for a completely different reason. The modernization of equipment designed in the late 1950s to work against 21st century threats is not a simple task. The mechanical part of the machine, the tracked chassis, the hydraulic actuators, 4 synchronized barrels, was created in the pre-computer era and is physically not designed to work with modern digital electronics without serious revisions. Nevertheless, a number of modernization programs implemented in different countries proved that the basic design allows such an update without replacing the machine entirely. In the framework of such programs, modern radar stations are mounted on the system, significantly superior in sensitivity to the original Tobol of 40 years ago. Optoelectronic sighting systems are added, allowing for visual fire with high accuracy even without the use of a radar, that is, without the very limitation that the crews faced back in the Afghan mountains. The key element becomes a digital computer, replacing the obsolete computing device of the Astrov era. Modern electronics is capable of processing data on targets that in the late 50s were not considered at all as a threat. Reconnaissance unmanned aerial vehicles, loitering munitions capable of attacking with hovering in the air, and other small, slowly flying objects. Here it is worth drawing a simple parallel. A car of half a century ago, originally designed without a single electronic control unit, can be equipped with a modern fuel injection system, electronic ignition, and sensors, significantly increasing its characteristics without replacing the basic body and engine. This is exactly what they do with the system. They change the brains and eyes, preserving the mechanical basis proven by decades. Separately, one episode discussed in the professional community of specialists in technology deserves mention, although it remains at the level of unconfirmed reports. We are talking about the story associated with the interception of a cruise missile of the Tomahawk type on the territory of Syria by one of the modernized versions of the system. There are no reliable official confirmations of this episode, and it is worth treating it precisely as a rumor. But the very fact that such stories are generally seriously discussed by specialists in relation to technology of almost 70 years of age speaks of the main thing. The platform, designed for a completely different era, still has sharp teeth against threats that Astrov and his colleagues in the late 50s could not even suspect. There remains one main question, for the sake of which, in fact, it is worth telling this whole story from beginning to end. Let us return for a second to the very beginning of this story, to the person with a stone in his hand by the side of a high-speed highway, who physically does not have time to hit a passing car. This very problem, the gap between the target speed and the reaction speed, is what made the designers of the late 50s take on a practically impossible task. Almost 70 years later, one can say with confidence the task was solved. Moreover, it was solved so successfully that the machine created then continues to serve in armies around the world, having passed through sands, mountains, and city blocks of 3 completely different decades and 3 completely different types of conflicts. But if you think about it, what exactly is the secret of such survivability? The answer will turn out to be much simpler than could be expected. It is not in any one ingenious detail, and not in a successful coincidence of circumstances. It is in the very principle laid down by Astrov initially, extreme simplicity of design in combination with intentionally redundant rate of fire. 4 barrels instead of 1 or 2 created a density of fire that, at the time of design, seemed to some specialists redundant. Why so many if the task is simply to hit the plane? The answer to this question was given by the very history of the machine's operation. It was this redundant density of fire that turned out to be a universal tool where the accuracy of an individual shot was inferior in importance to the variability to quickly cover an entire zone with fire, be it the airspace over the position, the slope of the gorge, or the upper floors of urban development. The simplicity of the mechanical part, in turn, provided repairability in conditions very far from factory floors, in the desert, in the mountains, on the city outskirts. A machine that went out of order could most often be repaired by the forces of field repair units, without waiting for shipment to the factory. And today, in the era of low observable targets, reconnaissance unmanned aerial vehicles, and loitering munitions, the same principle, high density of fire, as the most reliable answer to a high-speed and hard-to-detect threat, again turns out to be in demand. The system, designed for one specific task in the late 50s of the last century, has not become a museum exhibit. It has become a platform that time after time manages to fit into another new tactic of small conflict, remaining relevant where far more complex and expensive systems sometimes yield to it in practicality. The formula of this machine's longevity turned out to be surprisingly simple. Do not chase after excessive complexity where reliability and speed are enough. And, judging by everything, this formula will work for far more than one decade.